Hi everyone. So welcome to today's domain-driven design study. So today we'll be looking at part 4 of our study, which is relating domain-driven design with other domains or with other design pattern. So this course has been very interesting. It's a very wonderful book. And I would like you to study along as usual. So as usual, we read chapter by chapter and then we come together to summarize and review what we have learned, and then we continue to the next chapter. So that's the pattern we have been following, and that's the pattern we'll also continue with today. Okay, so let me set it up and bring everything on board. I don't know why my laptop is slowing this morning. So it has not been behaving like this. Okay, so we are here. All right, guys. So we have part 4, relationship to other methodologies and patterns. So how does DDD relate to other patterns and design principle? So we'll start with microservice, and after microservice, we'll continue to other one. So now let's study this microservice for like 10 minutes, and then we'll come back for summary. All right, let's go, guys. So if you are just joining us for the first time, please do like and subscribe to our channel so that you can study this with us every day, UTC plus one, like every 4:30, but I started a little bit late today because I am just waking up. I was very tired yesterday. All right, guys, let's study along. Okay, guys, so this is chapter 14, microservices. So, in software architecture, we have two type of design pattern based on these microservices. We have monolithic architecture and microservice architecture. So monolithic architecture combine all domains, all business domains into one pack and don't just deploy them together. So there's no separation of concern, there's no bounded context, there's no contract. So everything is just combined together and they cannot be separated. So if one domain fails, if one domain logic fails, every other logic fails along. The microservice is modular and it is functional. So it gives room for bounded context and separation of concern. So in microservice, you can separate each domain logic. You can deploy application independently of each other, and then they can still work together as a whole, even though they are separate from each other. So each application can be deployed independently of each other. And you can, you can deploy as many codes as you want. You can write many codes. You can write one application in Python. You can write the other one in Java. You can write the other one using Node. You can write other one using C# and still deploy them together and they will function. So that is microservice. It allows you to build modular software, modular design pattern, and still deploy them into the same platform, and they will still work individually. And if one domain fails, it does not affect the other domain. So I think microservice actually give rooms for what is known as the bounded context. That is, each domain logic is limited to that, is contained in their own microservice. Okay. So micro refers to the public interface, not code. So micro is just here is just maybe like the user interface where you see where you experience each application or in practice, or it can be a database. If you design a modular architecture, for instance, you also have a modular database. Every application will have their own database, just like we have in agentic system design. Every agent have their own database. So agents are actually microservice in nature, because every agent have their own ID and their own database, and they can function independently of the other agent. So a good service hide is database and implementation. Of course, there's always this separation of concern. You don't combine front end with back end and with database. No, you have to, or in networking, there's what we call the private network and the public network. So anything that you want to expose to the internet, you deploy it on a public network, and anything you want to hide from the internet, you deploy it on a private network. Okay. So all database and backend should be deployed on a private network, and then the front-end application, the user interface that you want to expose to the public, will be deployed on a public subnet inside your virtual network. Okay, so that's how it works. So a good service hide its database and implementation. Database and implementation and backend are always hidden in a public subnet that is not accessible to the internet, that is not accessible to the public. So optimize overall system complexity, not each service in isolation. So when you want to optimize microservice, so you have to optimize overall system, optimize the backend, not each front end, because whatever you do in backend we also apply to every front end application that is sitting on the backend. So when you optimize the backend, it automatically take effect on the front end. Subdomain usually provide safer service boundaries than aggregate. Aggregate is just like you have taken you have taken some logic from each domain, and then you aggregate them and bring them together as a whole, as a combination of logic for the business enterprise. So here in aggregates, we have said that you should design your domain based on the business complexities. So know when to use aggregate and know when to use a modular architecture, know when to use bounded context. So subdomain usually provides safer service boundaries than aggregate. So let's put it in terms of monolithic and microservice. Microservice is better than monolithic architecture when it is well designed and when the business maturity allows it. Why? Because you can build individual domain, you can build application based on individual domain knowledge and then deploy it independently of each other. So subdomain microservice architecture is safer than aggregate architecture if it is well designed, if there is room for boundaries, if every application, every domain operates within their boundaries by not interacting with other domain. And if they must interact at all, you know that there must be a contract design for that. Avoid turning every CADABA function into a separate agent. So remember that in agentic system design, there is what we call tool, there are functions, and they are agents. So agents are not function. Functions are designed to solve a particular problem. Functions are just like mathematics formula that must be applied to solve a particular problem. For example, in differential equation, there's what we call the Bernoulli equation, there's Riccati's equation. For example, a problem that you can use Bernoulli equation to solve, you cannot use Riccati's equation to solve it because they are designed for different type of problem. So also agentic function in agentic system design. You design a function to solve a particular problem. So because you are designing a function to solve a problem, you cannot call that function an agent. No, a function is not an agent. An agent can combine many functions together to solve a particular problem. For example, let me take this as an example. For example, I want to build a data engineering agent, for instance. I will have injection, maybe the data is coming from a document. Okay, so I will have an extraction agent, an agent that will extract the data from the document and process it and store it in the raw layer as is, and then I will have an agent that will transform it, transformation logic and everything, and then store it in the silver layer. Then I will have an agent that will build a model, star schema or snowflake from the transformated data and then store it in the gold layer. Then I will have another agent that will build a data max or a reporting table from the gold layer and then connect it to Power BI. And then I will have a visualization agent that will actually visualize the data in Power BI where I will see my reports live. So for example, each of these stages, you can design an agent for them. Then inside each stage, for example, extraction, for instance. So you will not say that you want to design an agent that will extract information from document A, another agent extract information from document B, because they are not the same document. Another agent extract information from document C. No, you can't design agent. You just have one agent that will extract everything from various documents, irrespective of their form. And then now, talking of extraction from various documents, because they are not the same thing, you will now have to design a function inside the agent that will be extracting this information from each document. You have a function for document A function for document B, a function for document C, a function for document D, and so on and so forth, so that whenever each document arrives, the agent know which function to call to extract the document. So that is how it works. So do not turn functions to agent. They are not agent. They are just, a formula for agents to solve a specific problem. Okay. So that is microservice. So you can call functions. Functions are modular and they're also microservice inside an agent. Then you have microservices of agent. You have many agents with various you have many agents with various domain, like extraction agent, ingestion agent, extraction agent, transformation agent, or loading agent and visualization agent. Those are agents. Then inside the agent, you have various functions that help them to solve problems. Okay. So this is how microservice apply to agentic system design, and then you can apply this in your practice. Microservice is very interesting I've not read a whole book on microservice, but I've read a book on distributed system. And after this, probably we'll be studying microservice together, and then we'll see the whole application. So we'll study one of these popular Orally book. Okay. Yeah. So let's move to chapter 15, where we have event-driven architecture. So if you are just joining us, please kindly like and subscribe to our channel so that you can study with us every day, study many books. Now we are studying domain-driven design. So when we are done with this, we'll move to microservice. And when we are done, we'll probably be studying a book on unified theory of cognition. I like that book. I like that book because I told you I'm writing a book cognitive architecture design for multi-agent system, and it's a very, very fantastic book. That's why I'm reading many books. So I've read a lot of books, about 10. So this is just like the 12th one. So let's study together, guys. Please like and subscribe. Thank you. All right, guys, so let's look at what we have in chapter 15. We have event-driven architecture. So we've talked about communication pattern in the previous chapter. In chapter, I think that was chapter 4. Chapter 4. So there's a chapter that talked about communication pattern, business modeling, and architecture pattern. Okay, design for heuristic or evolving design, event storming, and domain driven. Okay, so we talked about communication pattern in one of the chapters where we talked about synchronous, asynchronous, out of the box, saga, CQRS, and other ones that we talked about. So here we want to look at event streaming. So for example, I think we've talked about event streaming before, or event sourcing. So event-driven architecture. So once you say something is an event, it means that, as you know, you are putting in your data, you are getting the result immediately. And yes, and then I used e-commerce to explain. Now, when you place an order and pay for your order, the order gets submitted, and then it is processed, and then a delivery man pick it up and then deliver it to you. So the event is not complete until your order gets to you, and then you like the order. So that is when the event finishes. So event is just like a real-time application, real-time information, where you send an information and then it is processed immediately, and then it is delivered to the destination where the information is supposed to be delivered to. So for this kind of design, Kafka can be used, publisher and subscriber, where a topic publishes a message, and then the subscriber subscribe to the message, get the message, and deliver it. So if the message is not delivered, there's what we call dead letter queue, where it can be dropped or it can be reprocessed again, depending. So in Azure, you can use Azure Service Bus for this. We can use um Azure this thing. There's what we call message queue, or Azure message queue as well, can also be used, or Azure event grid to handle everything in and out. So these are ways that you can design for real-time information, real-time streaming. Event is used for streaming. It can be real-time or near real-time. So EDA integrate services. So this is event-driven architecture. That is EDA. EDA is the short form for event-driven architecture. So EDA integrate services, event sourcing, record internal history. So event-driven architecture integrates services together in real time. And a good example is Azure Service Bus. Or you can, if you want to open source it, you can use RabbitMQ or RabbitMQTT or Kafka, for instance. So they integrate services in real time. They pass information from one application to the other in real time. So event sourcing record internal history. Command request action while event describe completed occurrence. Like I told you, an event is not complete until, the message is delivered, the event is delivered, and then it is closed. That is when an event is complete. For example, in real-time or data engineering, you are streaming data live from the source from an API, then processing it in real time, ingesting it to the database in real time, then you are seeing the analysis on your dashboard in real time. So the event, when the data is collected from the source and then being streamed, being processed, that data will not, that process will not end until the dashboard is updated. So an event is not complete until the message is delivered, until the whole process is finished. Notification, state transfer, and domain events serve different purposes. So we have notification. So an example of design for notification is a RabbitMQ. where a message is delivered as a notification is delivered as a message, and the RabbitMQ carry the message to the destination. And then when the message is delivered, it gets eliminated from the whole process because it has been delivered. So also Azure message queue also work that way. When one message is carried and delivered, then it is deleted from the system, except when it is not delivered, they stored as dead letter queue, and then you can reprocess it. So Azure Service Bus can also be used. Exposing private domain events create implementation coupling. So there, because you are streaming an event in real life, does not mean that you should also expose what you don't need to expose to the public. Your database must also be kept at the back end. It must be secure. It must be kept on a private network. It is not everything that you need to expose. Only expose what is needed to be exposed. Okay, so you can implementation coupling. So you can build a decoupled architecture. Event sourcing is good for when the architecture is decoupled, when they are separated from each other. But when they are tightly coupled, event create implementation coupling. That's you have to still link everything together through a one event. CADABA consumer must undo delay, duplication, and disorder safely. So if you watch some of my videos on multi-agent system design, where I talked about multi-agent communication pattern between multi-agent system, where we talked about the Saga pattern, the CQRS, and then also event source and Kafka and the RabbitMQ and all of that. So we said, a dead letter queue does not mean that the message is dead. It means that, it is not delivered, and then you should check what is there and look at it and reprocess it. Okay. So CADABA consumer must undo delay. So you must design your agent to undo delay, to undo duplication, and to undo disorder safely by using dead letter queue to store undelivered messages. Or you can also design to undo delay. For example, design for a reprocessing. When a message is delayed, design that other agents should wait for the message to come before they continue the processing of that particular order. And then design for duplication, or make sure that an event is not duplicated. So make sure there is no duplicate message, no duplicate event. Everything have their own ID. If the agent have ID, agent should have ID, tags should have ID, even messages should have their own correlation ID, so that you can trace every message, every event that is being performed in your agentic system design. So this is event-driven microservice. You can try to implement it in your system and see how it works. So now, please, if you are just joining us, please kindly like and subscribe to our channel, so you can study with us every day like this. Thank you. So let's look at chapter 16, data mesh. We'll read together like 5 minutes, and then we'll come back for summary. All right, guys. So let's look at chapter 16, data mesh. So data mesh is just like, it is derived from data warehouse principle. So data mesh is, knowing the data and be able to build a data into a data product that is fit for use, that is fit for analytics, and fit for visualization, and fit for each domain. So data mesh is just like building a data model for a particular domain. That's what data mesh is all about. So data mesh apply domain thinking to analytical data. It has four principles. The first one is the composed data ownership around domains. Data mesh okay, let's start from beginning. So in data engineering, data engineering is the process of building ETL pipeline to get data from source to destination and then connect the data to a business intelligence tool for visualization. So data ETL means extract, transform, and load. That is, get data from source, transform it, and load it into the warehouse, and then connect it to analytics. And then we have two types of data platform. We have OLTP, we have OLAP. OLTP means um, online OLTP. Okay, so online uh transformation processing or online transaction processing. I just mean it means online. Okay, so let's see what it means here, guys. Let me not do something. Okay, so we have OLTP and OLAP models. So OLTP is normally real time. The OLTP are transaction data, online transaction processing. That's what it actually means, online transaction. So it gets data in data is stored in real time from source to the database. For example, an example is a finance operation where you use ATM, whatever you call it, is withdrawn from your account, then your balance is updated in real time in the online database. It normally uses online database like Azure SQL database, um, or Oracle SQL database on cloud. All those are online database that can be used for transaction processing. OLTP is real-time transaction processing. Why OLAP are historical data? OLAP means online analytical processing. They are both online, one in transaction, one is analytics. So OLTP is online analytic processing. It collects data from the OLTP database and then process it and transform it and model it into the warehouse where you can connect it to analytics. So for example, organizations normally have two types of databases. They have OLTP, which is where real-time transactions are being stored. Then they have OLP, which is the warehouse, where the historical data are collected from the transaction database and stored in the warehouse for visualization. So OLTP data mesh actually built on OLTP because warehouse, you have many data in warehouse. All the organization data is stored in the warehouse. Okay. So OLTP supports analysis, optimization, reporting, machine learning, data science, and so on and so forth. So that's what we have. So for OLTP, we have what we call the data lake. Data lake is where you have all the raw data from OLTP, all raw data collected from OLTP database, API, streaming, and so on and so forth. Every raw data are collected and stored in data lake, and data lake can become siloed if you don't manage it very well. So when you are building data lake, it is better for you to build or create a container. For example, I've been working with Azure for like 4 years now. So let me use Azure Data Lake Gen 2, for instance. So inside Azure Data Lake Gen 2, you have for storage. You have blob storage for storing. It can store files. It can store objects. It's objects, video, or file, audio, and so on. Then you have the file storage, which is usually is used for storing any files like file data or like virtual machine files and so on. You can store them in file storage. We have stable storage, which is used for storing key value data that are not structured. We have the message queue, which is used for storing messages, just as we have discussed in our event-driven in the previous chapter. So that's what you have in data lake. So what I want to get here is that when you want to store organization data in data lake, organization have many domains, and then inside those domains you still have subdomains. So it is better that you create a container for each domain, so that each domain data is bounded within that container. So if you are creating you want to collect data from HR, from IT, from finance, from procurement, from supply chain, or from production, from wherever the data is coming from. It is better you create a container for all of these domains. Create a container for HR, create a container for you know, create a container for IT, create a container for finance, create a container for procurement, create a container for supply chain, create a container for production department, create a container for a manufacturer, every other department that you have. Create a container for each of them. Then inside those containers, you can now have subdomain. Maybe under IT, you have the operation teams, you have the security team, you have the information and data team, you have everything. You can now create maybe files or folders, folders inside those containers for the subdomains. So also in other department, so that your data will not be siloed, so that when you want to access the data of each domain, you can always go into each data lake to access this data. So, and then we have the warehouse. So warehouse is used for storing processed, transformed and processed and properly modeled data. And in the warehouse, you have the two types of model. You have the star schema and the snowflake schema. So the star schema have maybe one fact table or joined to various dimension table. Fact table stores, every business informations, every business numerical information, while dimension table store the description of those numerical information, and they are connected by through what we call primary and foreign key. Every dimension table have their primary key, and those primary key serves as foreign key in the fact table. Then Snowflake is more denormalized, where you further break each dimension table into further fact and dimension table. So in Snowflake, you can have more than one fact table joined to many dimension. Dimension table can serve as fact table in Snowflake schema, okay? So which is a little bit more complex than star schema. So data warehouse centralized transform analytical data. Data warehouse just serve as a single source of truth where you have all domain data stored. So in data warehouse, instead of storing all the organization data under one schema, you can create a schema for each department. For example, IT, we have their own schema. Finance, we have their own schema. Procurement have their own schema. Supply chain have their own schema. Human resources have their own schema. And every department will have their own schema. So inside this schema, you can now start creating data marts, which is reporting table. Data marts are reporting table, or like a data product that you can give, that you can connect to Power BI to visualize. So data marts are just small reporting table created from a transform table, or created from a model table that is, it's meant for analysis. It's meant to be connected to Power BI, so that you can just connect and model what you want to model and build your reports for presentation. So data mart address focus, analytical need, visualization need, basically. So traditional warehouse also often often violate operational boundaries, just as we have said. To put operational boundaries into consideration, design schema for every domain so that you can identify them. So also for data lake, create a container for every domain to solve that problem. So uncontrolled data lake become data swamps. So if you don't clearly build container and folders for your data, you'll be building a data swamp, and then to access the data will become a problem. Okay, so even though data lake is centralized, you should still build it with bounded context, build it on domain based, and create a container folders for each domain and subdomain, so that you can know where to find the data when you need to use it. So data mesh apply domain thinking to analytical data. So data mesh help data engineer to apply domain thinking. For example, if you want to, process data for procurement, you will apply the domain thinking of procurement into that data. If you want to build a data lakehouse for, finance, for example, you will apply finance domain thinking so that you will not merge finance data with HR, so that you not model finance data the way you want to model HR data, and so on and so forth. So it has four principles: the compose data ownership and around domains. So that is why even before you build data warehouse, you need to gather requirements. So requirement gathering is always very important. Gather requirement from every domain experts. Okay. Then the compose data ownership around domains. Treat data as a product. Treat it as a product. Okay. In software, we treat every software we build as a product. So also when you are building a data model, treat the data model as a product. Treat each domain data as a product that is meant for that domain. Enable domain team autonomy through a self-service platform. So there should be domain team autonomy. That is, each domain must be able to work without depending on another domain. So make sure there's a self-service platform. For example, that's why I say in Lakehouse, in your data lake, create a container for every domain, and then inside the container, you can now have a folder for subdomain. Okay, that's domain autonomy. So that if there's somebody in in the domain, in the department, or in that domain that needs to access the data, I will give them fine great access. I'll give them access to the container that they need to access. And then if they just need some folder in the container, I'll give them access to only that folder. So it creates autonomy so that domains do not depend on each other. So also in the warehouse, so that's create a schema for every domain and subdomain, so that when you want to give access, you give access to only the schema, only the domain schema, not the entire organization schema. Okay, so that's how it works. And yeah. So establish federated governance and interoperability ecosystem. So when you treat data as a product, and then you build with bounded context, then you will be able to practice federated governance. You role-based access control. You give access only to you give access based on what is needed. You give access based on domain. You give access based on subdomain. Okay, so you will not be given access to everything you have in your warehouse or data lake to everyone in the department. So that's what data mesh is all about. So let's look at our summary note. OLTP support operation, while OLAP support analysis and learning. Of course, we've explained that. Fact records business activities in numerical form, while dimension describe these business activities. Warehouse and lake become fragile when they depend on private schemas. Okay. So do not build warehouse and lake to depend on private schemas. Have a schema for every domain and subdomain. Okay, data mesh give domain team ownership of analytical data products. So when you implement data mesh in your platform building, so you will be able to give fine-grained access to every department based on what they require. So it gives every domain ownership of analytical data product without exposing every other domain data to them. CADABA need governed data product for evaluation and application. So there's what we call agentic mesh. I'm still reading that book. It's one of already published book. It's very interesting. So you should find it and also read it. So I told you that agentic system built on data engineering. So we have data mesh. We also have agentic mesh. Agentic system are also product. They are treated as a product in software engineering. Okay. So agentic mesh means that every agent is a product, and every agent have their own data mesh. So agents are domain. So in multi-agent system, you have you have many agents solving domain problem, and then inside that domain you have subdomain. So agent can be attached to every subdomain to solve the domain. Then when they collect their data, they are indirectly forming data mesh. So we have agentic mesh and we have data mesh. So CADABA need governed data product for evaluation and adaptation. So also when you are building agentic system, you also need to implement data mesh, because agents are also mesh. They are domain they are domain and subdomain specific. So also you also need to implement data products, because every agent have their own data products, okay, and they have their own databases that they write into. So this is what data mesh is all about. So CADABA analytical facts. So how do you apply this to cognitive architecture design for autonomous business agent? So make sure you have analytical facts like task completed, policy violation detected, human approval requested, two execution failed, compensation completed, business outcome achieved. So dimension can include agent, model, tool, policy, tenant, workflow, risk class, and time. This product can support agent evaluation, model comparison, process intelligence, or cost optimization and future learning. So these are very, very interesting, guys. They're very, very interesting. So that's that about data mesh, and it is very interesting. So make sure you implement it when you are building something like this next time. All right, so this is the chapter 16 is the last chapter, and what a very interesting chapter, because I'm a data engineer, so this chapter is very interesting to me. I feel like reading it on and on and on and on and on again. So closing word, guys. Central message. Kolmogorov closed the book by organizing DDD around 3 stages. So the man Kolmogorov organized this book around 3 stages. The first one is problem. Understand the business domain, strategy, subdomain, and language. Make sure you understand business domain, strategy, the subdomain, and language. And you can only get this from the domain experts. So you need to go to them, gather requirements. If they don't like kind of understand it, you can design Q&A before you go to them. So when you answer them question, it expand their thinking, and then they will be able to give you advanced answer to expand the business knowledge. Then solution. Select useful models, bounded context, appropriate design patterns. So make sure you select useful model that applies to the domain. Then implement bounded context. Okay, so build for the domain, not for the entire organization. Then appropriate design pattern. Use appropriate design pattern. Use appropriate architecture. Use appropriate communication pattern. Use appropriate event-driven or batch processing pattern. Use appropriate language. Use appropriate database. Okay. Implementation. Apply the pattern pragmatically. Evolve them and integrate them with microservices, events, and analytical data. So when you are implementing the architecture, you know the problem in number one. Two, you design the solution, and then you want to implement it. So do not implement based on what the business will be in the next 5 years. Implement based on what the business, where the business is now. And then when the business expand, you can involve them, you can integrate them in with microservices, events, and analytical data. So in other words, if a domain does not need to be event driven now, there's no need of making it event driven. Okay, make it batch or build it as it is now, so that when the time comes and event driven is needed, you can expand and evolve the architecture to accommodate that. Okay, and then also implement analytical data. OLTP is a must, because you always have them when you have transaction. If it's involved transactional, you need OLTP, but you always need analytical data, because you have to analyze what is coming from your system. You derive understanding of the system through visualization. Okay, so the principal lesson is to understand the reasoning behind domain-driven design rather than follow its pattern as dogma. So do not make it an adopted practice, dogma. You should follow its pattern and apply the patterns where it is needed. Do not apply all pattern because you say, oh, this is domain driven, so let me bring domain driven practice here. No, it may not apply. So you have to study the pattern, pick a pattern that apply to your problem, and then use the pattern painstakingly. When uncertainty remains, return to domain experts. So when you are not sure of what to do, then you have not quite understand the problem. So you need to return to domain or experts. to gather more information. Maybe you've not used Q&A, or maybe in your Q&A, you did not ask the right question. So you need to go back to them and ask the right question, and then, gather more understanding. Sometimes you may even need to study. You can get a book to study and understand the domain. Okay, so if you can get information from the domain expert, you can learn their domain, what they are applying. Everything is written, guys. There are textbooks and textbooks out there. For example, I wanted to learn process intelligence and business process management. So I work with someone that procurement manager that I've asked questions, that doesn't really give me what I want. So I have to go to these books to study process intelligence and business process get the information, and then apply it, in my principle, in my data engineering, because I'm a generalist data engineer. I'm not specific to particular business. Okay. So when uncertainty remain, return to domain experts, the ubiquitous language and event storming. So you may need to return to ubiquitous language, the business language, or you may need event storming. You may need to gather all the experts, all the stakeholders together, and then brainstorm on what to do. So this is the end of this book. And then we still have the appendix. So we'll study the appendix together because we have to finish it up. Study the appendix together tomorrow. All right, see you tomorrow, guys. Thank you for listening today. If you are just coming, please like and subscribe so you can study along with us. You can also watch other videos that I have in the catalog. I have a foundation mathematics for machine learning there. I'm a mathematician. I have BSc and MSc in mathematics, of course. So, and I'm also a developer. I write Python, by a little bit of C# and Java and Scala. Scala is a functional program, which is also very useful for me. So my main languages are Scala and Python. This is the age of AI, guys. So I also use a main stack to build a full stack machine learning application, AI application, and agentic AI system. So I also run a consulting business. You can check our website below to check our services and contact us if you need any solution built for you. Thank you, guys. Bye for now.